And get started. In today's lecture, we're going to talk about earthwork computations. So, the earthwork computation is very important for any engineering project. And earthwork involve the determination of volumes of materials that to be excavated or embanked or filled. So, prior to the construction, we need to have a certain level for the project. And in order to achieve this level, we need to cut some part and fill some part. And we call this earthwork computations. So volume computation are also needed to determine the capacity of tanks and reservoir and to get to check the gravel and other materials. So the volume computation, not only for earthwork computation, but also if you want to know the capacity of tanks and reservoirs, and also if you want to check the amount of a material, for example, gravel. So this process is very important. For example, here we have this reservoir. So in order to know the capacity of this reservoir, also volume computation is going to help us to know the capacity of the reservoir. And in how to determine the volume, we have various methods in order to determine the volume. We could use the cross sections, and we could use the spot levels, and we could use the contours. I'm gonna show you all of this method, how to determine the volume using these methods. So the movement of soil or rock from one location to another for construction purpose, we call this earthquake. Already I introduced this concept to you. So if you are going to move soil or rock from one location to another for construction purposes, we call this earthquake. And this movement, it could be excavation or it could be embankment. So a volume of earth is excavated, which means that removed from its natural location. We call this cut. So if you are gonna remove the soil from its natural location, we call this cut. And on the other hand, the excavated material, it's going to be placed and compacted in a different location, and we call this embankment or fill. And the cut and the embankment, we call this earthwork. So the earthwork, it could be excavation or it could be embankment. So here we place a soil here. We call this embankment or fill. So how to determine the volume of the material? So we know that a solid figure is one that occupies three-dimensional space, and the three-dimensional being the length. We're going to have the length, we're going to have the width, and we're going to have the height. So in case we have rectangular solid, so in this case the volume is going to be L times W times H. So a rectangular such as this box here, it could be a box or a slab of concrete, has 6 panels or faces. So here we have 3, and we have other 3 on the opposite sides. And the volume V of the rectangular solid is simply the product of its three-dimensional, which is the length, the width, and the height. Also, if the shape is different, not like that, we have other formulas to determine the value of the volume. If you have prism, if you have a cone or a part of a cone, if you have cylinder, we have mathematical formulas in order to determine the volume, like sphere and like cone. But we know that in the field, we are not gonna find the shape is not going to be exactly like that. So we need to find convenient method in order to determine the volume. So we usually if we are going to have to construct a road, then constructing a road is going to involve a lot of cut and fill. So you remember last time we introduced to you, if you have a road, then we are going to have profile and we are going to have cross section. So the view from here is the profile and the view from here is the cross section. And the cross sections are useful in determining the quantities of cut and fill. So I'm going to introduce you how to use the cross section in order to determine the quantities of cut and fill for or in construction design. We know that the cross section is going to be here, and cross sections defined are a series of elevations taken at right angle to a base line at a specific station. Whereas, so here the cross section, we could have cross section also here and there. While the profiles is from here, from this view. So profiles are a series of elevation taken along a base line at some specified repetitive station interval. So here we have the profile and here we have the cross section. So here we have the cross section and the length inside here is a profile. Again, here we have the cross section and here we have the profile. Here we have cross section and here we have the profile. So here is a typical section. We usually make the section like that. Okay, because if you make the section like that, this part is going to collapse. So we usually make the section like that with slide, with a slope. Because if you are going to make it vertical, so this part is going to collapse. So usually we make the cross section like that with a slope. So this one is not going to collapse. So the again, we say that the cross sections are a series of elevations taken at right angles to a baseline at a specific location. Here we have a typical cross section. We call this line here is the original ground surface, and we call this the formation level. So here is the original level for this cross section, and this one is the formation level. And we call this here the formation width. Okay, 2B is the formation width, and here we have the plan width, 2W, and the distance from here to here is the height, and it should be measured at the center line of the cross section. So here is the center line of the cross section. The value is H is going to be measured from here to here. And like I said, we usually make a slope like that, and the slope is going to be defined as the vertical unit over the horizontal unit. So here, one represent the one unit in the vertical direction, and this one represent the length in the horizontal direction. The slope side is always defined like that. So this one, it could be 1, 2, 1, 3, 1, 5, and so on. It's mean that every one unit in the vertical direction is going to be corresponded by S unit in the horizontal side. So here we have the height of the cross section. 2W here represent the plan width, and 1W represent the side width. Here we have a figure for a road that should be constructed through this mountain. So in this part, we need to cut, like you can see here, we are going to cut a part of this mountain. Then in this part here, we need to cut a part of that mountain, but we need to fill on that place here. We need to fill a soil here. While from here to here, we need to fill on both sides. So here we have cut, then we have transition point on other hand, on one side we have a cut, and on the other side we have fill, while in this part we have only fill. So here we can see the profile for that road. Here we have a number of stations across the profile. We have 16, 17, and so on. And here we have the elevation. So through the work of leveling, we'll be able to provide this profile. We know the levels. So the natural or existing level look like that. And the road that is going to be constructed is going to be like that here. Here we have the proposed grade line. So the road is going to be constructed on this grade line. So what we will do in this case, it means that in this part here, we need to have a fill, while in this part we need to have a cut, so that the road is going to be constructed along this proposed grade line. So we're going to take a section, for example, at this station 18. When we are going to cut a section, the section is going to be look like that. Here is the existing level, the ground, and in order to reach this proposed baseline, I need to have a fill. If I'm going to cut here, at this station, here we have the ground level, and here we are going to have the proposed level. So in this case, I need to cut this part. This part needs to be excavated. So this situation is opposite to that situation. In this situation, we need to have a fill, and in that situation, we are going to have a cut. While in this point here, we are going to have two parts. A part that need to be cut, and a part that need to be filled. This here is a transition point, like this one. Like here, we have a part need to be filled, and a part need to be cut. So here we have a transition stations. So we have first here we have a part completely need to be filled, and here we have a part which completely need to be excavated or cut, and here we have a part in the middle transition stations. We have a side that need to be filled and other side need to be cut. And determining the cross section and understanding the cross sections is going to help me to determine the volume that need to be cut and the volume that need to be filled. So again here we have this road like that, and again the road here we have the center line for us. So we're going to say that the project is going to start from here, and the start point has been defined as 10 plus 0, 0. 10 mean 10 kilometers plus 0 meters. So here is the first station. Then we have a station here. It has been defined as 11 plus 0, 0. 11 here, it means 11 kilometers. So the distance from here to here is 1 kilometer. 1,000 meters, the distance from here to here. So we have a station here, and we have a station here, and so on. The last station is 13 plus 0, 0. So the distance from here to here is 3 kilometers. So here we are going to have a part which need to be filled and a part which need to be a cut, and also we're going to have transition stations. So we're going to note that from the station 10 plus 0, 0 up to the station 11, up to this station 11 plus 21. In this, between these stations, I need to fill, right? So we need excavation, or we need to have a fill between here and here. In order to reach to the formation level, I need to fill here and so on. And then from this station, 11 plus 21 and 11 plus 64, here we have transition point. Okay, from this station and to that station, this part need to be filled and this part here need to be cut. So here we have transition stations. Then from this station here to that station here, I need to have excavation. Excavation is required from here to here, and filled is required from here to here. And here we have a cut and fill. So now we are in a position to introduce the first method to determine the volume. We call this end areas method. And if this method can be compared to the trapezoidal rule for areas. Remember in the last lecture, we discussed the trapezoidal rule. So in trapezoidal rule, we are gonna determine the average offset between two offsets, and then it's gonna be multiplied by the width between them. So this method is similar to the trapezoidal rule for areas. So here, if two cross-sectional areas, A1 and A2 we know them, are known for us here. Assume we have this volume which need to be determined, and then we know the area 1, the end area here, and the end area there, and also we know the distance between the two sections. Then the volume is going to be given with this formula. The volume for this land here is going to be D. D represent the distance between the two sections times the average area. A1 is the area of one end, and A2 the area of other end. So this one is very simple. If you want to determine a volume for a certain land, then the volume is going to be D times A1 plus A2 over 2, which means that we are going to determine the average area from the one end and the other end, and then should be multiplied by the distance between them. So if we have this project here, and here we have this volume which need to be filled. Here we have the ground or the original ground, and here we have the proposed level. So we need to determine the volume need to be filled here. So at this station 8 plus 0, 0, I should determine the area here. Okay. And also I should determine the area at station 9.00. So this represent A1 and this represent A2. Then I need to determine the average. The average is going to be the area at this end and the area at that end over 2. Then are going to multiply this by the distance between them. Since this is 8 plus 0, 0 and this one is 9 plus 0, 0, that means the distance here is 1 kilometer, which means that 100 or 1000 meters. This is how we determine the amount of materials that to be filled here. Sometimes I'm going to have more than one end areas. So in this example here we have A1, A2, and A3. So again, this method is comparable to trapezoidal rule for areas. So in order to know how to do this, then we are going to determine the area for this part and the area of that part, and then I'm going to sum them together. So the area for this part, the first part, is going to be A1 plus A2 times over 2 times D1. And the area for this part is going to be D2 times A2 plus A3 over 2. Then the total is going to be this one plus that one. But this simple process is going to lead us for n number of cross sections. If I'm going to have a number of cross section, I will be able to determine this using this rule. I'm going to add all of the areas, all of the volumes together, the volume of this part plus the volume of that part, and so on. So V1 represent D1 A1 plus A2 over 2. Then V2 represented by D2 times A2 plus A3 over 2, and so on. And this one is going to be Dn minus 1 represent the number of the last area. So if this is A3, then this one is going to be D2. If this one was A10, so this one is going to be D9. Okay, and n minus 1 represent the area next to the last area. If the value of n was 10, then this one is going to be A9. And here, of course, it's going to be A10. A10. And this one could be arranged more. So we can add this section plus that section. Then if D1 is the same as D2 as D3, then we are going to have a common factor, which is D. So we can take D over 2 as a common factor. Then we are going to end up with A1 plus AN plus 2, A2 plus A3, and so on. And this also could be arranged to be like that. V total is going to be the D. D is the distance between the end areas times A1 plus AN over 2 plus A2 plus A3 plus A4 until the area next to the last area. So this formula here is similar to the trapezoidal rule. Instead of using offsets, here we are going to use end areas. That is why in the before we talk about the end areas method, we say this method is comparable to trapezoidal rule. Just instead of using offsets, here we are going to use areas. Let's see example about the determining the volume using the end areas method. So in this example, it says that compute the volume of fill between station 0 plus 400, where the section area equal 123 meters squared, and the other station, which is 0 plus 500, and the area at that station is 234 meter squared. So here we have the first station, and here we have the last station. The area at this station is given here, and the area at that station is given there. We need to determine the volume of fill between the two stations. So this one is very simple. We are going to use the formula directly. Here we have only two sections. So we are going to say that the volume is going to be D times A1 plus A2 over 2. The value of D is the distance between this station and that station. Remember here, the first part represents the distance in kilometers, and this part represents the distance in meters. So obviously the value of D is going to be 100. This one minus that one. The value of A1 is given here, and the value of A2 is given here. So I'm going to plug the number inside the formula. So this one is 100, this one is here, and this one is there, and we can compute the value of the volume. So the problem also could be a little bit complicated. So in this example, we have only fill, and this also could only be a cut. But for the example to be a little bit complicated, we are going to have cut and fill. So in this example, they say that at the station 0.600, the cross-sectional area is 100 meters squared of a fill. So here we have at this station here, we started with a fill. And at the station 0 plus 700, the area is 150 of a cut. So we started with the area of a fill and we end up with the area of a cut. Okay, so this example, we started with a fill and we end up with a cut. And also he give us additional information. He says that the grade point is at station 0 plus 635 meters. So the grade point is the point where we don't have either fill or cut. So at this point, the fill is going to over and the cut is going to be started. And he says that what is the volume of cut and fill between these stations, between this station and that station. So first, we are going to determine the volume of the fill, and then we are going to determine the volume of the cut. But we need to know that the grade point here, at the grade point, the fill is over, which means that the volume is going, the cross section at that point is going to be 0, because at the grade point we don't have either fill or cut. So in order to determine the fill for the first part, I'm going to start here and finish here, but the area at this station is going to be 0. Then I'm going to start from this station to that station, but the area here, which to be started, is going to be 0. So first, I'm going to determine the volume of the fill between this station and the grade point. And the value of fill is going to be the distance between them, then the distance from here to here, this one minus that one, which is 35 meters, times the area in the beginning, which is 100, and the area at the grade point, which is 0. And that is going to give us the volume for fill. Then we are going to determine the volume of cut. The volume of cut is going to be between the grade point, and between this station, 0 plus 700. And again, the area here at the grade point is going to be 0, and the area here at this station is going to be 150 meter squared. And also I need to know the distance between the grade point and between this station. It's going to be this one minus that one. Okay, so the volume for the cut is going to be 65 times 0 plus 150 over 2. Here we determine the volume for the fill and the volume for the cut. Now I'm gonna move to more complicated case. So here we need to determine the earthwork quantities, which means that we need to determine the volume for the cut and volume for a fill. So here we have earthwork quantities for a section of a roadway indicate a transition from fill to work to cut. So here we need to determine the earthwork, but we need to remember this. He said that we have a transition from fill to cut, which means that some stations we are going to have a part which need to be filled and a part which need to be cut. And the following areas are scaled from printed cross sections. And he says that using the average end areas, which means that the methods that we have introduced, what is the total required fill and cut volume for this project? So in this project, we have transition from fill to cut. Everything starts with the fill, and then we have transition between fill and cut, and then we have a cut. So here we have the stations. The project starts with this station, which is 20 plus 0, 0. The area for the cut, none, and the area for the fill is written here. So at this station, we have only area for fill. Okay. Then at this station, the cut started here. So the cut here was 0, but after this station, we are going to have a cut for one side, and we have a fill on the other side. So here we are going to start the transition period. Here we are going to have transition period. Then at this station, here we have cut area and we have fill area. So here we're still within the transition period. Then we have this station here. Also, we have cut and we have fill, but the fill finished here. So the value of the volume for the fill is 0 because here the fill finished at this station. And in the final station, we have only cut and we don't have fill. So we need to determine the earthwork quantities. We need to know how much volume for cut and how much volume for fill. So what we will do, we are going to construct this table here like that. Here we have the stations. I need to create empty row between two consecutive stations. Empty row here and empty row here and empty row here and so on. Then I'm going to fill in the number of stations and the area for the cut and the area of the fill. Here I'm going to create new column for the length, the links between two stations. And here I'm going to determine the value of the volume cut, and here the value of the volume fill. So I'm going to start with the first station, the first two stations. This is the first station, this is the second station. Here I don't have any cut area, and also here I don't have any cut area. I have fill area at this station and I have fill area at that station. So in this, between these two stations, I'm going to have only V fee. I'm not going to have V cut. Okay, I'm going to have only V fill. I'm not going to have V cut because the area here is 0 and also the area here is 0. First, I need to determine the length between these two stations is going to be this one minus that one, which is 10.5 meters. Remember, in order to determine the volume, we say that the volume is going to be D times A1 plus A2 over 2, right? So L here represents the value of D, the distance between the two sections. Then in order to determine V cut, the area for V cut is 0 here and 0 there, which means that the value of V cut is 0. Then I'm going to determine the value of volume fill. Here I have area for a fill, and also here I have the area of a fill. This one represents A1 and this one represents A2. So in order to determine V fill is going to be the D, the value of D times the average area. This one plus that one over 2. So this one is 0 and this one is this value times the average. This one A1 plus A2 over 2 times the value of the D. Then I'm gonna move for the second station and the third station. I'm gonna focus on this and on that. First, I need to determine the value of D. Okay, here it's written as L, but this one represents D in the formula. First, the value is gonna be this one minus that one. It's going to be the value of L or D in a formula. Then I need to determine the volume for the cut. So here we started with 0. The cut started here, but here also I have the value for the cut. So this one represents A1 and also this one represents A2 for a cut. So the volume for the cut is going to be the value of L times the average area. This one plus that one over 2. And here we are going to have the volume for the cut. Regarding the volume for fill, it's going to be this one plus that one over 2 times the value of L. So this one plus that one over 2 times the value of L is going to give me the volume for fill. So between this station, we have transition stations. We have a part need to be cut and a part need to be filled. Then we are going to move to the volume between station 3 and station 4. So here, first I need to determine the distance between the two stations. So this one plus that one is going to give me the distance between the two sections. Then I have area for cuts, A1 and A2, and here we have areas for fill, A1 and A2. So I'm going to apply the formula for the cut and the formula for the fill, like we have done earlier in this step. So in order to determine the volume for the cut, it's going to be the distance times this one plus that one over 2. And for the fill, we are going to have the distance times A1 plus A2 over 2. And remember, since this one is 0, which means that the fill is over at this stage. Okay, so now I'm going to move to the volume between the 4th station and the 5th station. And in this step here, we don't have volume for fill because this one is 0. Okay, and this one also is 0. Here we don't have any part need to be filled. We have only area for cut, which means that here we're going to have only volume for the cut. So I'm going to repeat the process again. I need to determine the distance between the two stations, this one minus that one. And then I'm going to multiply this one times the average areas here to get the value for the cut. And here the value for the fill is going to be 0. Then after I finish from this process, I'm going to sum all of this together because this one represents the total volume for the cut. And I'm going to sum all of this together because this one represents the total volume for the fill. So the total required cut volume for this project came out to be this number. And the total required fill volume for this project came out to be this number. So this is how we determine the volume for cut and fill in a project like that. Also, we have another method need to be introduced to determine the volumes. Also, this method, we need to know the cross sections. And we call this Prismoidal formula. And in this formula, the Prismoidal rule assumes that the Earth forms a prismoid between two cross sections. We have with D apart. So here we have, again, in this method, we are going to use the cross sections. Here we have A1 and here we have A2. And D represent the distance apart between the cross sections. And in order to apply this method, we need to form something called mid-section. So mid-section here should be formed. We call this AM. Okay, we call this the mean area. So in this method, not like the end areas method, in the end area method, in order to determine the volume, we are going to determine the average area, right, between A1 and A2, and then multiply them by D. But in this method, we are going to form a mid-section. We are going to form a mid-section, and then we are going to determine the area for that mid-section. Okay, so how to form this mid-section? The mid-section is not the average area. The mid-section is the area that has been, its dimension has been determined as the average of dimension of the first area and the second area. For example, the height of the midsection is going to be h1 plus h2 over 2. Okay, and the width here is going to be the first width plus the second width over 2. So the mean area has been formed as a result of average dimension of the corresponding areas, the two areas. And this method is going to give us very nearly correct volume of earthwork. So this method is more accurate than the end areas method, because we are in this method we are going to create this midsection. So after we create the midsection, the volume can be calculated as follows. The volume is going to be L. L is the distance from the first section to the midsection, or the distance from the midsection to the last section. the value of L. Then it's going to be divided by 3. Then we are going to multiply by A1. A1 represent the first area, plus 4AM. 4AM is the mean area. We discussed how to determine the mean area, plus A2. A2 is the area here. Okay, so in order to use the Prismoidal formula, I need to create a section at the middle between the two areas, and then I'm going to use this formula. So A1 and A2 are the two end areas, A1 and A2. AM is the area of a section midway between A1 and A2. And we need to remember this, AM is not the average of A1 and A2, but is derived from cross-section dimensions that are the average of the corresponding dimension required for A1 and A2 computation. Like I explained earlier, I need to determine the dimension of that midsection from the corresponding end areas. For example, the height of the midsection is going to be H1 plus H2 over 2, and so on. And if you are going to use D, we know that here the 2L's equal 1D. So if you want to use D here instead of L, we are going to put D over 2. So we are going to have D over 6. So you could use L or you could use D. Also, this formula, it could be generalized for if you have a number of areas. If you have n number of cross-sectional areas, we can use this formula. The volume is going to be L over 3, then times A1 plus AN plus 4 summation of even areas plus 2 summation of odd areas. And you must have guessed this one is similar to Simpson's rule. Instead of using offsets, we are going to use areas. Okay, and also again, to use the Prismoidal rule, the number should be odd, just like the Simpson's rule. So here we have example. In this example, we need to compute the volume using the Prismoidal formula. Here we have the end areas, the first end area and the last end area, and we need to determine the volume using the Prismoidal formula. So we're going to use this formula here from here. Okay, but the problem is how to determine the value of AM. The value of D is given, which is 17. The value of A1, we can determine the value of A1 from this dimension. Here we have trapezoid. This dimension plus that dimension over 2 times the distance between them is going to give us A1. While A2, this dimension plus that dimension, the parallel 2 dimension over 2 times the distance between them, which is 3. But now what about AM? In order to determine the value of AM, a midsection here should be created. And the value of this length is going to be this one plus that one over 2. And the value of this height is going to be this one plus that one over 2. And the value of this height is going to be this one plus that one over 2. Then after we determine the dimension for the midsection, then we are going to determine the value of EM depends on these dimensions. So the value of A1, which is here, is going to be this dimension plus that dimension. These are two parallel dimensions over 2 times the distance between them, which is 7. Then in order to determine A2, this dimension plus that dimension, these are two parallel dimensions over 2 times the distance between them, which is 3. Then to determine the value of AM, we need to create the corresponding dimensions. We have AM here, this dimension is going to be referred to as AM, is going to be this plus that over 2. Of course, if this one is 0.75 and this one is 0.75, the value of AM is going to be 0.75. Then we are gonna also determine the dimension here. It's going to be referred to as BM. It's going to be this dimension plus that dimension over 2. And also I need to determine the height of the midsection. It's going to be this height plus that height over 2. Now I created the dimension for the midsection. If I know the dimension of the midsection, then I'm in position to determine the area. The area is going to be this dimension plus that dimension over 2 times this dimension here. So this one plus that one over 2 times 5. So now we determine the value of AM. So the value of V is going to be calculated by just plug in these numbers. And again, remember, this method is more accurate than the end areas method. So finally, we are going to determine the volume, but this time we are going to use the spot heights. In the previous two methods, we use the cross section areas. In this method, we are going to use the spot heights. And we usually use this method in case that we need to have a large deep excavation, such as basements and underground tanks. So this method, we usually use this method in case that we need to excavate to create basement or underground tanks. So how to use this method? We need to create a square, rectangular, or triangular grid. We need to form grid on the ground. And the spot levels are taken at each grid intersection. So we need to create grids like this. It could be made from rectangles and triangles and so on. And then at each grid, at each intersection like that, we need to evaluate the reduced level. The reduced level need to be evaluated at each cross section. So the first step in this method, we need to create a grid. The grid could be made from rectangles, from triangles, and so on. And then we need to determine the value of, we need to determine at each intersection, we need to determine the reduced level. So the number here represent the reduced level at this point and that point, and so on. So if you are going to take, for example, this part and draw it in 3D, it's going to be look like that. 4.67 represent the distance from here to here, and 3.21 represent the distance from here to here. The level here represent the formation level. This one represent the formation level. So let's say that I need to create a basement at a reduced level of, let's say, 2 meters. So this one represents the formation level. So in order to determine this length, actually, this one is not the reduced level. The length from here to here is the difference between the existing reduced level and the formation reduced level. So I'm going to determine the reduced level at this point, and I know that I need to excavate to existing or to a formation level, which is, let's say, 5 meters. Then the difference between the reduced level at that point and this point is going to give me this height. We call this depth cut. So this value represents the depth cut at each and every point. So in this here, these numbers represent actually the depth cut, not the reduced level. Okay, so here these numbers represent the depth cut. And in order to determine the depth cut, I need to know the reduced level, existing reduced level, and also I need to know the formation level. The difference between them, they are going to give me the depth cut. So if these numbers represent the depth cut, then this number is the distance from here to here. Okay, this point is the existing point level, and this one is the formation level. I need to excavate from this point to that point. Here also I need to excavate from this point to that point and so on. So let's say that I need to determine the volume only for this part. So the volume for one part, this part like that, is going to be determined by the main height times the plan area. I need to know the plan area and I need to know the mean height. How many heights do I have here? I have 4 heights. This one and that one and that one and that one. So the main height is going to be the summation of all this height over 4 if I have 4 heights. If I have 3 heights, then it's going to be divided by 3. And the plan area here is 10 times 10. 10 times 10 represent the plan area. So the volume for this is going to be the mean height times the plan area. But this is only for one spot, for one part. I need to do this for this part and for this part and so on. Okay, so in order to use this method, I need to know the formation level. This one is the formation level at each grid point. I need to know this. And the distance from here to here represent the depth cut. And in order to get the depth cut, I need to know the existing, I need to know the existed reduced level. So the difference between the existed reduced level and the formation level is going to give me the depth of cut. Then after I determine the depth of cut at each intersection, I will be in a position to determine or to use this method. I will be in a position to use this formula here. Now, in case that I need to determine the volume for all of these spots without determining the volume for this one plus that one and that one, we have one formula help us to determine the volume for the whole grid. We have one formula help us to determine the volume for the whole grid. This formula here is only for one spot, for this part only. But this formula help us to determine the volume for the whole grid. So how to use this formula? So the formula says that the total volume is going to be A over 4. A represents the volume only for one spot, not for the whole grid, only for one spot, which is 100 here in this case. Okay, then it should be multiplied by the summation of the single depth. Here we have single depth, double depth, triple depth, quadruple depth. So the single depth, a depth that is not going to repeat itself. So for example, like H1. So H1 here is not going to repeat itself. Why? Remember, this formula is a summation for this formula here. So in order to determine the total volume, I need to sum this part plus that part, plus that part, plus that part, plus that part. So this height 2 is going to be repeated twice. It's going to be involved for determining the area for this part and also for that part. But what about H1? H1 is not going to repeat itself, right? We are going to use only H1 to determine this area for this spot. But H2 is going to be repeated twice because I'm going to use H2 in order to determine the area for this part and also for that part. So H2 is double depth, while H1 is a single depth. Then what about H6? H6 is a common between this one and that one and that one and that one. So H6 is quadruple because this depth is going to repeat itself 4 times. Then what about H5? H5 is a double depth because this depth is common between or mutual between this one and that one. Then what about H7? H7 is mutual between this one and that one and that one. So H7 is triple depth. What about H11? This one is single, because this one is not mutual with any spot, only for this spot. What about H10? H10 is double depth. It's mutual with this spot and that spot. So once you understand what does it mean by single depth and double depth and triple depth and quadruple depth, then you will be able to use this formula. So remember, the value of A is a plan area for one grid area, for one spot, for only one spot, not for the whole grid. So now let's see this example so that we can use the formula for the whole grid. So here we have this grid. It has been created so that we can determine the excavation volume. We have a grid of 9 points. We have A, B, C, D, E, F, G, H, and I. And this dimension here is 25.5 meters, and this one is 30 meters. And we need to compute the excavated volume in cubic meter. Remember here, he says that the numbers at the grid points represent the depth of cut. Is very important information. The number here represent the depth of cut, because sometimes this number is going to represent the reduced level at that point. In this case, I need to know the formation level so that I can determine the depth of cut. But this is easy for us since the number here represent the depth of cut. So we need to use this formula in order to determine the total volume. So the simple method, I'm going to determine the volume for this spot and for that spot and for that spot and for that spot and sum them together. Okay, but here I need to use only one formula to achieve that. So I'm going to use this formula to achieve this without determining all of the areas and then combine them together. So here I need to know the value of the area. The value of area, remember, it's gonna be for only one spot, which mean this length times that length, not the whole area. Okay, you need to remember this. Then you need to sum the value of the single depths. So here, how many single depths do I have? I have 4. I have A, and I have C, and I have G, and I have I, because these points is not mutual with any spots, only for this spot here, and this one only for that spot, and so on. So I'm gonna have this plus that plus this and plus that. This represents the summation for single depths. Then what about the double depths? I have the B is going to be repeated itself twice. I have D, I have F, and I have H. I have 4. So I'm going to have this one, that one, and that one. Then what about the triple depths? Here I don't have any triple depths. So the summation is going to be 0. Then what about the quadruple depths? I have only one quadruple depth, which is E, because E is mutual between this and this and this and that. So I have only 12.94. So I have this number here. Then I'm in position to use the formula. I have all of this. I know the single depths, double depths, triple depths, and quadruple depths. And the value of A, I need to, this 1 over 2 times this 1 over 2 is going to give me the area for one spot. So here we have the area for this spot plus this one, this one, this one, and that one. Okay, this one is going to be multiplied by 2. This one is going to be multiplied by 3, and this one is going to be multiplied by 4. And here is the area, the volume for this grid. This volume needs to be excavated in order to create a basement or reservoir. Here we have Another example, this one is similar to this example, but I created this example so that you can understand the idea of the depth of cut. So in the example number 4, this number represent the depth of cut. The depth of cut is this depth. This depth represents the depth of cut. But sometimes you are going to have only the reduced level for this point and the formation level. In this case, I need to subtract this one plus that one so that I can get the depth cut. So I created this addition example so that you can understand this idea. So they say that calculate the volume of earth to be excavated. And he says that the excavated level is 10 meters. So this one is 10 meters above the sea level. This is the excavated level. You are going to excavate so that you can reach the 10 meters. And the numbers at the grid points represent the level from each point. So this one here represent the reduced level, the existent level. Okay, is the existent level for this point, for that point, and for that point, and so on. So the depth cut is not given in this example. So I need to determine the depth cut. The depth cut is going to be the existed reduced level minus the excavated level. So this one minus that one is going to give me the depth cut. So I'm going to apply everything like in example number 4, but in this example I'm going to subtract 10 from I'm going to subtract the value of the excavated level from each and every elevation at the intersections. So this one minus 10 for all the heights. So I'm going to apply this formula again. Nothing is going to change, except that instead of putting 16.45, this one is going to be subtracted. I'm going to subtract 10 from this value, and from this value, and from this value, and from that value, and so on. Just like that. I'm going to apply everything. The only difference is here in the previous example, we have the depth cut, and here we have the reduced level at each point, and we have the excavated level. I'm going to follow the same concept. So now we are going to move to the last example. On this example, we need to determine the volume need to be excavated. And we create this grid. We created this grids, and here he says that the numbers at the grid point represent the depth of cut. So since he says it, it means that I'm not going to subtract anything. Okay, so the numbers at the grid point represent the depth of cut in meters. So in this case, I'm not going to subtract anything. I'm going to apply the formula. Okay, here we have the formula. I need to know the value of A, and the value of A is going to be 100 meters squared, this one, for one spot. Okay, then I need to know the single depths, and the double depths, and the triple depths, and quadruple depths. For this example, regarding the single depths, I'm going to have H1, H4, and H8, and H11, and H9. So I have this one, that one, and this one here, and that one here, and that one. I'm going to have 5 depths. Okay, then I need to look for the double depth. For the double depth, H2 is going to be double, H3 is going to be double, H5 is going to be double, and H10 is going to be double. So I'm going to have this, and this, and this, and this here. Okay, now I need to look for the triple depths. Regarding the triple depths, I have H7, this one. I have only one. And finally, I need to look for the quadruple depths. I have only this one here. Okay, then after I identify all of this, I will be in a position to use the formula. Just plug in the numbers, and here we are going to have the total volume. So also it's very important to solve this. It's very important problem. Solve it like a homework problem. I'm gonna send you the solution later on. So in this example, I'm not going to be able to use the formula directly. Why? Because here I have triangle and triangle here and another triangle here. And here I have rectangle, while here I have squares. So this one is a little bit complicated. I'm going to apply the formula only for this part, for 1, 2, 4, 5, and 6. Then I'm going to apply the formula alone for this part. Here I'm going to apply, remember, the mean height times the area. The mean height is going to be this one plus that one plus that one over 3 times the area of triangle. And I'm going to treat this separately and this separately and also this separately. Why this part is going to be treated separately? Because the area of this part is different from the area for this part and that part and that part. So the general formula is going to be applied only to this part, okay? While the formula for one spot is going to be applied for part 3, 8, 10, and 7. So I'm going to stop here regarding this lecture. If you have any questions, please